PowerPoint. And, let's see, new kid is here today. Oh, yeah, I think I recognize him from someone. Okay, good deal. Good to have you back. Okay. All right. Now, we've well past example 1, but let's get the slideshow set up from current slide. And we'll begin there. But let's start with the announcements. Most of these you've heard before, but I do have a couple of others to say too. I hope this is over with, but they sent out this last week. I haven't seen them take it off. It says, reminder, the business office is in the process of closing out data for financial reporting. Please do not, this is written to us, not to y'all, do not add or drop courses for students, award or process grant aid, complete registration until further notice. Okay? I hope they're letting people do that now because it's getting awfully close to second mini-term, so we need to move on that. The last day for first mini-term is this coming Friday, the 11th. That means that is midterm, or sometime over the weekend is midterm. And that means that, number one, if any of you are planning to take a second mini-term class, or if you know of someone who is, the last day to, classes begin for second mini-term next Monday, a week from today, okay? And your midterm progress reports are due in by next Wednesday, a week from Wednesday, which means I need at least some score from you, either a research paper or your first test. So please try to get something into me before next Wednesday. Okay? So, that's from the administrative calendar. From the volleyball calendar, today is the 7th. On Wednesday, volleyball team will be hosting Sneed State Community College at 6 p.m. Over on the Birmingham West campus. So if you're over there, please cheer them on to victory. They are a really good team. Go see them play. All right, this I think is over with by now, so I'll recycle that. This is coming up Wednesday and Thursday. A scholarship summit. Okay? Are you an upcoming graduate? I know all of you are, maybe not this year, but most of you may be this year. Do you have plans to transfer to a university? I'm guessing you probably do, at some point anyway. Unsure how to pay for the remainder of your education? I'm sure y'all got that down pat. Come educate yourself on college transfer process and transfer scholarship opportunities available from some of the leading colleges in the state. And this will be Wednesday in the U Building Academic Success Center auditorium on the Birmingham West campus, which is right across the street from East campus. That'll be from 1 to 3 o'clock Wednesday afternoon. Then on this campus, it will be Thursday down in the faculty staff dining room, which is just next to the cafeteria, and that will be from 1 to 3 in the afternoon as well. That will be on Thursday. Here are some of the participants: Alabama A&M, Alabama State, UAH, Birmingham Southern, Jacksonville State, Tuskegee, Miles, University of Alabama, Tuscaloosa, UAB, Mercer University from over in Georgia, Sanford University from Birmingham Homewood, University of West Alabama, University of North Alabama, Mississippi State University, and University of South Alabama. Success is where preparation and opportunity meet. These are sponsored by the Career Services Department, Counseling Services, and the Space Center. Okay, so please plan to take advantage of that as you can. This is one, and you can check with Fred here. He's participated. The NASA Community College Aerospace Scholars Program is taking applications through October the 16th. That's just over 2 weeks, no, less than 2 weeks from now, just over a week from now. So please, if you're interested, here's information, here's websites, places to go, where to get the applications, all that kind of stuff. So please take advantage of that It's a great program, right? Is that where you were? Yeah. How'd that go?
It was great.
Okay.
Yeah, it was awesome. It was just like a week long. We get put on a team and then just like build rovers and their competition and everything. It was really fun.
All right, super. Any reporting and presentations on it?
Yeah. And each team member has like a different thing you do. And, like,
Right.
I was the person that basically had the presentation at the end.
Had the what?
I had the presentation at the end.
Oh, good.
That was like my job.
Oh.
Each team member had a job. That was my job.
Okay, did you get any pictures or?
Yeah, I got quite a few pictures.
Okay, because we probably want to use that documentation for student learning stuff. Okay, so who's your advisor?
Aisha.
Oh, Lewis, Miss Lewis. Okay, good. Yeah. So if you will get her documentation on that, because she'll be collecting stuff like that. We're trying to do a better job of getting those things now rather than having to rush at the end of the year into it. All right, let me get Jeremiah marked here, and there you are. Okay, 6 people. Yeah. Okay, good deal. Let's close that out, whatever that is. All right, we're on in Chapter 8, Integration Techniques and Improper Integrals, mostly integration techniques. 8.2 is integration by parts. We got going on this pretty well last time. And page 526, example 4. So let me get my pen set up, and we'll do example 4. Find this, the integral of x squared sine x dx. Okay? What's the first thing that comes to mind to solve that integral? Where would you begin? How would you start? Anybody? Hopefully somebody would start. Any ideas? Help me, somebody. Any techniques, procedures, tricks that you would use to try to solve it? What's the title of the section? Anybody? Oh, Dawson decided to make it today. All right. Top part of the alphabet's doing quite well. One person's holding up the whole bottom half of the alphabet by himself. Okay. What would you do? Where would you begin? Oh, long weekend, huh? Anybody, help me.
I know you're supposed to use U substitution.
Second?
You're supposed to use U substitution for the first part.
Yeah, we usually don't call it U substitution here, though we do say let U equal. That is a good beginning. And it kind of is a U substitution. But you see, with this one, what technique are we using? Title of the section? Integration by parts. So we break it into two parts. A U part and a DV part. Okay? Those are our two parts. Okay? Now, that's your first choice then. Because there's nothing you can do to do this one straight off. There's no U substitution that will work, just U substitution. Doesn't fall under any of our basics, so we have to do something. So since it's a product of two pieces and is not a perfect integral, if it was, we just integrate it. But it's not, So we're going to break it into two. One is a u part and one's a dv part. Now, the u part we're going to differentiate. The dv part we're going to integrate. Okay? Now remember, usually when you differentiate, things get easier. Not always, but usually. When you integrate, usually it gets a little more complicated. Okay? So we want to pick our parts such that one part will get simpler when you integrate it, when you differentiate it. The other part doesn't get any more complicated when you integrate. So which part will be what? Which you want to integrate, differentiate, and which you want to integrate? Two parts up there. Parts is parts. Huh?
Let's integrate the sin x dx.
Okay. He said we'll do our dv to be sin x dx. And the reason for that is it doesn't get much worse. It gets to be a cosine, and it probably has a sign change, S-I-G-N sign change. But other than that, it's not too much worse. And that would make your u x squared. So what do we do next? Then, say again? Okay, du is equal to 2x. One more thing. Dx. And v would then be
Cosine.
certainly a cosine, except one more little thing. Say again? It's a negative. No, don't add any c's to it yet. We'll deal with that at the end. Okay? Everybody okay with this so far? Okay? What would this produce how does this contribute to solving that integral? You start with the functions, u and v, and just multiply them together. They happen to be negative here, so that would be a minus x squared cosine x. And then you would do what? Subtract the integral of your bottom line, or at least the way I write it is the bottom line. Okay? Well, that has a minus in it anyway, so that's going to make that a plus. And let's pull out the 2, because I don't think we need that in there anymore. And then you have an x cosine x dx. Okay. This part is through. You've integrated that, it's come out, it's there. This is an indefinite integral, so we can't do anything else with it. But don't forget about it. Don't lose it. It's there. Keep up with it. Now we have a new integral. Can we integrate that one?
You said integrate?
Not. Say again?
You said integrate?
Yeah. Can you integrate that new integral then? It is simpler than the first one, but you still can't integrate. Do the process again, okay? So here we'll start with, do you mind using the same letters? Okay, so see, we're not actually putting them in, we're just using them to rearrange, okay? So we'll let u equal what? X, very good. And dv equal? Cosine x dx. Okay, then what's next? du is equal to dx, perfect, and v is equal to sine x. If you're differentiating, it'd be a minus, integrating is a plus. Sine x. All right. And where do we go from there? Again, multiply the two functions together. Now, don't forget about the first one. You still have the minus x squared cosine x. Now we have plus x sine x. Okay? And then we have a minus the bottom line. And what's the bottom line there? the integral of sine x dx. All right. So that gives us, don't forget the first part, minus x squared cosine x plus x sine x. And what's the antiderivative of sine x? Second? Negative cosine x. So the minus will wipe out that and becomes a plus cosine x. And now we put our indefinite integral. Plus c. Plus c. Okay, wait till the last part to do that. Okay. Now, that should be the integral of the original thing or the antiderivative of the original thing.
We can find the antiderivative of the sine x dx, but we couldn't find the antiderivative of x cosine x dx.
Okay. Now, let's say that one more time.
We differentiated sine x of dx.
Right here? Right there.
But
Okay.
not x cosine x dx.
No, that was the first part. Remember the UV you just write down. Because you've taken them out of being a derivative. Okay? It's only the d parts that you integrate. These don't have d's in them. So you just write that down, just like we wrote them down here. X squared times minus cosine x. That was there. This UV is there. And you're left with just one integral left. And that's the bottom line here. Sine x dx. There was a minus there because you subtracted. Okay? Yeah, you remember why you subtract, right? Or not?
Cosine.
Well, no, not because of that. This whole process, integration by parts, comes from this. Derivative of a product, UV, is equal to what? Product rule.
Oh, okay. So it would be
Product rule. Taking derivative of a product. What do you get? Anybody? Anybody? Oh, that was last test. We aren't responsible for that anymore, are we? Sure we are. How do you do the product rule? A little louder. First times derivative of the second plus second times derivative of the first, right? So that would be u dv plus v du, right? Product rule, right? Now what we have at the very beginning is something like this, a u dv. Here's your u and there's your dv, okay? What is it? It is d of uv minus v du. That's where the minus goes from. Yeah, if you had u dv is equal to d of uv minus v du. I've written the product rule just, okay. Now, if you put an integral in front of each of these, okay, this is your original problem. That was it. Okay? Well, integral of a differential is just uv. That's why there's no integral sign with that. That's just your uv. And then you got minus v du, whatever's left. That minus sign came from the fact you're subtracting from the product rule. Okay? Is that making sense?
I would just ask. That makes sense.
Okay?
I'm curious. So on the second part of the equation, yes, that's
Somewhere over here.
yeah, at the very top. Why did we do it? Why
we started here, okay? This was our UDV here that we're trying to integrate. And we broke it into a UV, so it became a UV, that's this, because the V was a minus cosine, okay? That's where that came from. Minus VDU, that was your bottom line here. The 2 was out front, and I think I left off my 2 somewhere. Y'all let me get away with it, didn't you? Shame on you. Shame, shame. Okay? There was a 2 right there in front of all that mess. So this would be a 2 here and a 2 here. Now, we don't have to put a 2 in front of the C. Y'all are going to let me get away with that, aren't you? Okay. Now, sorry. Just realized that. Got it off my 2. Okay? So you did that. But when you got to this form, the UV minus VDU, which is what that is, you still can't integrate this. Not directly. So you do it again. Okay? And keep this part, because that's still part of the problem. Okay? And then you break this down into a U and a V, and that 2 is in front of that. Okay? So this is the X sine X out front. That's your UV minus, and then the integral that's left over is the bottom line, and that is a V du. It's just that. Well, that we can integrate. Finally, we got it down to something we can integrate, and that's going to be a negative cosine. But we have the 2 in front of it, which is plus, and you have a minus here, so minus and minus is plus 2 times cosine X, and then your plus C again. So that should be the answer. Let's see how the book did. Looks like they got minus x squared cosine x plus 2x sine x plus 2 cosine x plus C. Got it. They use a capital C. I usually use a little c. It really doesn't matter. It's just some constant. Okay. Now, here is a warning. And y'all did it quite nicely without having to be warned. But when you start, and let that be your U and that be your DV, and then you have to do it again, be sure you use the same parts. U is the polynomial part, and DV is the trig part. If you flip them, you're going to wind up back right where you started from, if you do it right. And that's not going to help you at all. So once you have chosen a path to go down, stay down that path. Don't back up and go back where you started from, and then you're no further along than you were. Okay? Good deal. Any other questions on this? Good questions so far. Okay. Now, if no questions, we'll go to the next one, example 5. Okay? So, example 5 here. Find this, the integral of secant cubed x dx. I don't want to quite say it this strongly, but I'm going to. Do you see a product anywhere in there? Say again? No, that's not a times. X is the argument of the secant function. Now, I thought you almost had it there. It's secant times. Say again? Say again? Yes, yes. There is a product in there, isn't there? That is the integral of secant x times secant squared x times dx. Okay. Now, here we have a little bit of a quandrum, dilemma, quandary, something. Corundum? No, that's not it. You want to take a derivative of one of these, and hopefully doesn't get too much worse, but you want to integrate the other one, and hopefully it gets better or no worse. Okay? Now, the question is either one of those a perfect derivative? If you were to integrate it, you get just a function. Secant squared x is the derivative of what? Yeah, not tangent squared, tangent. Just tangent. So that may be a good way to go. Okay, so all of our other little rules maybe didn't do too well. So what would you do? Let u equal something and dv equal something. What's it going to be what? Okay, I thought we just said the other way, didn't we? It, not as derivative, it is the derivative of something. So that should be our dv is secant squared x dx. So u would have to be secant x. Okay? That's not going to get a lot better, by the way. So this is sort of breaking some of our rules. Then, what's the next step? du is equal to, what is the derivative of secant x? Yes, that's gotten worse, and usually we don't want that to happen. Secant x, tangent x, dx. Okay? But what does our dv become? V is equal to tangent x. All right. Well, where do we go from here? Equal to u? Yeah. Yeah, so that would be secant x, tangent x. That's just where you write them, the product of those two down, minus, and what do you have left? The bottom line. No, remember? uv, when you take a derivative, is uv dv plus v du. So if you want to isolate this, you subtract the v du from it. So that minus sign is there, part of that subtraction of undoing the product rule, kind of, like, sort of. Okay, now you do your bottom line. What's your bottom line here? The integral of secant x tangent squared x dx. Now somehow that's actually looking worse to me. Yes? Okay. Where? Right here?
Did you just move that to the behind the integral?
Say it again now?
Did you just move that to behind the integral?
Okay. Okay. What I did, are you okay with this part down here?
Yes.
Okay. Well, then what you do is take the functions part, the u times v, that's what we did there, secant x tangent x, minus the integral of the bottom line. And the integral of that would be secant x tangent squared x dx.
Okay.
Yeah. Now, not looking too good, is it? The first part's not bad, but the second part actually has gotten worse. And we usually don't like it to be worse. Now, I was trying to think if any trig identity will help. And there is one that comes to mind. The first that comes to mind, the secant is 1 over cosine, tangent is sine over cosine. That gets you, oh, it may not be too bad, would it? Let's do that, now that I think about it. Because what does that give you? Don't forget this part. We're going to come back and pick it up later. Let's write this in terms of sine and cosine. What does this give us? Anybody? Say again?
1 over cosine.
Yeah. Oh, this isn't going to be as good as, yeah, that would be 1 over, I thought it was going to be better than this. It's not. Okay. It's going to be bad. Still bad. What is the top, the other one? Sine squared over cosine squared. Nope. If that had just been a sine, oh, that would have been fine. That would have been wonderful. We could do a U substitution and go to town. But that's a sine squared. So sorry about that. Not going to work the way I wanted it to. Forget that one. You didn't have it memorized anyway, did you? Okay. The only other trig identity I can think of that might have potential is this will be secant x minus times, and what in the world is there another trig identity that you can relate to tangent x? Yeah. Okay. You got the right idea, but I think you got them sort of in the wrong order. Say it one more time. It's not 1 minus secant squared. Secant squared x minus 1 dx. Okay. Again, this isn't looking very promising, is it? Okay? Because where that takes us is secant x tangent x minus the integral of secant cubed x minus secant x. I can, ooh. When you do secant x, don't leave out the c, okay? That's not a good thing, okay? Well, to write down in math class anyway. Okay. Now, on the one hand, it's not terrible, because once you get this part, that's the same as that part, you can add it to both sides. And this part is solvable, isn't it? I think. Maybe.
You can split them up.
You can look on the table, huh?
You can split those up, right?
Yes.
The integral of secant cubed x.
Right. That's what I'm suggesting. So this will be, let me write it all down. Integral of secant cubed x dx is equal to secant x tangent x minus the integral of secant cubed x dx, and minus and minus will be plus the integral of secant x dx. Now, this almost seems like cheating, and in a sense it really feels that way. But if you add this to both sides, then these go out and you have that. Now, how in the world do you integrate secant x? Now again, you might try 1 over cosine, but without a sign on top, that's not very helpful. But in the table, is that where you went?
Yeah, it's natural log of secant.
Exactly. Natural log of secant x plus tangent x. Okay. Okay, leave that one alone, and this will be the natural log of secant x plus tangent x. And here's where you put your plus c. Okay? Now, I need some more room because I can't write down here because I run into all this stuff. So I'm going to erase some stuff up top, if that's okay. Like this and that, even though this is integral to our problem. Aha, pun intended. Okay. But we've got everything written down here. I'll go on and erase this one too. Just leave that next line. Okay. Now let's add these things. this gives you 2 times the integral of secant cubed x dx is equal to secant x tangent x plus the log of absolute value secant x plus tangent x plus c. Okay? And then we'll divide everything by 2. Okay? We won't divide the c by 2. It's just going to be a constant anyway. So you get your integral of secant cubed x dx is equal to 1/2 secant x tangent x. You leave off the n, you get tax, and you don't want tax either. Okay, plus 1/2 the log of secant x plus tangent x plus c. Now, if you wanted to, you could do this 1/2 up to here, and that's fine too. This could also be written as 1/2 secant x tangent x plus the log of, you still need the absolute value signs here, secant x plus tangent x, square root of that basically, to the 1/2 plus c. Okay. See what they got. Secant, yep. The integral of that cubed is 1/2 secant x tangent x. They left it in the earlier form, 1 plus 1/2 log of absolute value secant x plus tangent x plus c. They left it in that form. They didn't do the log of the square root. So, tricky problem there. But in my mind, if you're going to the table to get the integral of secant x, which is what we did, why don't you go to the table and get the integral of secant cubed x? Well, it's not in this table, but it's in the next biggest table, the one that you find in the back of your book, in Appendix B, which is on A, let's see, A6 maybe? Yeah. Nope. Well, maybe it's not back here. Yeah. A5. Integral of secant to the nx. And that's, if you go and put it in, you'll see you wind up this very same thing. And it's almost as many steps using the thing from the table as what we did there. So integration by parts, good way to go. Any questions on that? That was a toughie, okay? Take some manipulation tricks to do it. Once they work, call them a method. Okay. Can I erase, or you need it a little longer? Everybody got it? All right, we're moving on to example 6. Okay? Finding a centroid. A machine part is modeled by a region bounded by the graph of y is equal to sine x, pretty popular graph, and the x-axis, okay, and this is obviously then going from 0 less than or equal to x is less than or equal to pi halves, okay, well no, not so obvious, but that's what you got, okay. It says find the centroid of that region. In other words, you're going to assume this is a very thin laminar plate, no density difference anywhere, so you're just going to integrate that. Now, remembering back from the last chapter, okay, what that, okay, the first part of this is find the area of that region. Okay, because remember, centroid has an X bar, a Y bar, and both of those are divided by the area. Okay, so let's find the area first. That's why they start there. So it's the area of that would be the integral of this. Okay, sine x from 0 to pi halves of sine x dx. I think we can do that without too much problem, can't we? With the antiderivative of sine. Negative cosine, evaluated from 0 to pi halves. What is the cosine of pi halves? Cosine of pi halves. Cosine of 0 is 1. Cosine of pi halves is 0. Okay, that would be a 0 part. And then you got minus a minus because you're doing the lower limit, and you have a minus out in front, so that'd be plus the cosine of 0. And what's the cosine of 0? That is 1. So that gives you 1. All right, our area is 1. Not going to be too hard to divide by that, is it? Okay, so all we have to do is now find your X bar and your Y bar. Okay. But they do the Y bar first. I don't know if there's any particular advantage to doing that first. I would say not. So let's draw the graph. And it goes from 0 to pi halves. There's the part that you got. Okay? Now, if you do the X bar, let's take dx's because everything's in terms of x's. The X bar, remember, for this strip, it's the area of the strip, which is just sine x dx. So now they call this the moment with respect to y, from the y-axis. If you like to use that terminology, that's fine. Moment with respect to y-axis, to me it's a little confusing. It's the area of that strip, which is, the height is sine x, and the thickness is dx, and then multiplied by the distance from the y-axis, which is x. Okay? So that's going to give it, that's the part we need to integrate to be the x bar. Okay, because the denominator is going to be 1. So let's integrate that. How can we do that? We've almost seen something like that already today. What's our procedure? Oh, and this is going from 0 to pi halves. I don't know why I'm now yawning. Okay, the morning's still young. I think what it is, I'm having trouble breathing because I'm sort of congested today. All this cold weather we're having, I mean, it's what? Early October and we're only in the 80s? What's wrong with this picture? Okay. And we actually had some of that wet stuff come out of the sky. That was unusual too. Okay. How do you integrate that? 2 words will answer that question. Pi parts, that's it. And how would you proceed? U equal x, dv is equal to sine x dx. Then du is equal to dx, and v is equal to you had it right the first time. Negative cosine x. Remember, derivative of sine is positive. The antiderivative of sine is negative. Because, yeah, blah, blah, blah. All right. So let's do your UV part here. And this would be x, only with a minus, cosine x, that's also evaluated from 0 to pi halves. Okay? Minus the integral of what? 0 to pi halves. Your bottom line here. What is that? Minus a minus is a plus cosine x dx. Right? Yay or nay? Too many sign changes, aren't there? Sort of like that traffic light is just flashing on you. You don't have time to move any. Okay? Let's evaluate the first. Okay? When x is equal to pi halves, minus x is minus pi halves, but cosine of pi halves is? Cosine of pi halves is 0. So the first part of that one's 0. But then the second part, when you do the minus a minus, it becomes a plus. When x equals 0, it's 0 times 1, which again is 0. So this one produces nothing. A big fat 0. A 0 on the front top side because the cosine pi halves is 0. 0 on the bottom one because minus x is 0. So that disappears. So what are we left with here? Antiderivative of cosine x. Not that bad. Sine x evaluated from 0 to pi halves. And what's the sine of pi halves? One minus sine of 0 is 0. All right, one of those two. All right, so that's just one. So my goodness, it looks like our x bar is equal to 1. Now that's sort of bizarre, isn't it? Okay? But that is indeed what they got. Now remember, this is 0 to pi halves. Pi halves is a little bit more than 3 halves, 1 1/2. So this will be a little bit more than 2/3 of the way down. Is that right? Yeah. 3 halves at 2 halves. Yeah. A little bit more than 2/3. So your x bar is going to be somewhere around this value here, just at 1. Okay? So let's go up and do our y bar. Okay, y bar is the, you do the midpoint here. Okay? You do the midpoint of that thing. You still do, and if you like the m sub x's, you can write them down that way. This will be the integral from 0 to pi halves, okay? And your area part's still the same. That's the sine x dx. But now your, how far are you from the x-axis? That's the m sub x. That's halfway up there. So that would be another sine x, but this time over 2. So I pull the 1/2 on the outside, and that other sine x, because the length of this is sine x, but you take half of it, so it's times a 1/2 sine x. 1/2 out here, sine squared x there. Okay. Kind of a mess, isn't it? Do you remember how you do this? If you're tempted to do a u substitution, resist temptation, because that's not going to help you in here. You have to have a cosine in there. If you're doing it by brute force,
isn't there a trig identity?
there is a trig identity. It's called the power reducing formula, if you remember that. And how did that go?
Cosine squared minus 1.
Say again?
Cosine squared minus 1.
Okay, that certainly is, no, it's 1 minus cosine squared. right idea, but it's not very helpful because then you got the same thing to mess with cosine, and you can't do it. This is that power reducing formula, which has to do with your double angles.
It's 1 minus cosine 2x over 2.
Now, does anyone want a quick review of how we got that? I can tell you do, don't you? Does anyone really care? I mean, or you just want to use it? Would you like to see where that came from? Be honest. If you don't, I don't have to do it. But if you're curious about it, it's pretty easy to do. Anyone curious about it? Sure? Okay. Well, here's where it comes from. One of the most famous Pythagorean identities, of course, is sine squared x plus cosine squared x is equal to 1. Right? Now, wish I'd have written it the other way. Another one, though, is cosine 2x is equal to, does anyone remember that one? I'm going to stop right here and start this over so it'll look a little better. I'm going to start with the cosine 2x. Okay. Cosine 2x is equal to cosine squared x minus sine squared x. Ring a bell or not? Do you remember cosine of a plus b? Do you remember that one? Cosine a, cosine b, minus sine a, sine b. Ring a bell? Okay, you got that one. So if a is equal to b, and this becomes 2a, this becomes cosine squared a, and that becomes sine squared a, right? That's where that one came from, okay? Then do the other one. 1 is equal to cosine squared x plus sine squared x. Now, I know we usually write it sine squared first, but it doesn't matter. Addition is commutative, right? All right. If we're looking for sine squared, then what we do is subtract this one, the top one, from the bottom one. So you get 1 minus cosine 2x, and when you subtract, these two go away, and you get is equal to, that's supposed to be an equals there, 2 sine squared x, then divide both sides by 2. And that's where you got that from. Was it too hard to go back and get? Okay, so that's where that came from. Well, you had a 1/2 out here already, and now you put another 1/2. That makes it a 1/4. And then you have the integral of dx, there's your 1, minus the integral of cosine 2x dx. Okay? Was that okay to cheat like that? I went on and pulled the 1/2 out front to go with the other 1/2 that was already there because you did the midpoint. Okay? And that gave you a 1/4 in front, and then we're doing the dx from your 1. I already pulled the 2 out. So dx here, and then cosine 2x dx. I think we can all do that one, can't we? Please say yes. Antiderivative of dx is, and these, by the way, are going from 0 to pi halves. 0 to pi halves. Okay. Antiderivative of dx is x from 0 to pi halves minus antiderivative of cosine 2x. Anybody? Antiderivative of a cosine. Sine, okay, and 2x. But then you have to undo a chain rule. If it was a chain rule, you'd multiply by 2. Undoing that, you divide by 2. Another 2 in the denominator. We're getting sick and tired of those 2's in the denominator, aren't we? Okay. Now, I need room to work, okay? Let me erase some stuff here. Let me erase this up here. We've already done that. Bought a t-shirt, all that kind of stuff. I hope you had already gotten that. I didn't ask you, I just assumed you had. So let's see what our answer turns out being. This is our m sub x is equal to 1/4 out front. And what is the evaluate x from pi halves to 0? What do you get? Pretty easy. Pi halves. So you have another 2 in the denominator. My word. Minus. Okay. And when, this is a little tricky, but I think you'll like it when you finally realize it. When you do 2 times pi halves, what you get? 2 times pi halves. Pi, okay, sure, okay, okay, pi. What's the sign of pi? 0. Minus, a minus, doesn't matter. Sign of 0 is, second? Oh no. Who did you take trigonometry? Okay, 0, all right. That one turns out 0 both ways. So, not worrying about that anymore. So we wind up with, where was I, right? Oh, okay. That's all we got. Okay? That's all we've got. So this becomes pi eighths. And your area was 1, so this is your y bar. It's pi eighths divided by 1. Well, pi eighths is, pi is about 3, and so it's about 3/8. This is 1/2, 3/8 would be somewhere here. So your centroid would be somewhere over here. Okay? 1 for x, and something a little bit more than 3/8 for y. So something right about there. And that looks about right because you got quite a bit under it, quite a bit, yeah. It looks reasonable. Pi eighths is your x bar. I mean the y bar. They did the y bar first. Yeah. Pi eighths is the y bar and 1 is the x bar. Good deal. Any questions? A little bit, not all that tougher, but just a few more steps because you have to do an area, which was easy in this case, and then do your moment with respect to y and the moment with respect to x. Any questions for our erase? All right, we're finally ready for the next slide. Oh, there it was. As you gain experience in using integration by parts, your skill in determining u and dv will increase, which of course that means do a lot of homework exercises, right? So your skills will increase as you gain experience. Okay, good idea, folks. Okay. The next summary lists some common integrals with suggestions for u and dv. Okay, so let's you decide. Okay, here's we got a power form, x to the n, and then an exponential form, e to the ax. Which of these do you think needs to be the u and which needs to be the dv?
X to the n needs to be the u.
U, absolutely, because every time you take a derivative, you reduce that exponent a little bit, one step. You may need several steps, but you can do it, and your dv would then be e to the ax. Now, sure enough, every time you do that, oh, I'm sorry, they're doing a bunch of these at once. Or x to the n times either of your sine or cosine functions. In both of those, u will be the power function, and your dv will be e to the x, sine x, or cosine x. And here's why. When you integrate an e to the ax, you get an e to the ax times 1 over a, but can't avoid that. But those are just constants. Don't make it worse. When you do a sine ax, you get a cosine ax over a. That's okay. And when you do a cosine, you get a sine. So those don't get any worse. These get simpler when you differentiate. Okay. When you have a form like that, what do you reckon you're going to do? In this case, because I can't integrate log x, I got to differentiate. And that gets simpler. What is the derivative of log x? Please tell me you remember. Yeah, 1 over u, okay? 1 over x. So that's what you let to be your, that. Now this one, sure enough, gets worse, okay? X to the n. It gets worse, but you see it goes to x to the n plus 1, right? But this, when you differentiate it, it goes 1 over x. That's x to the minus 1. So those cancel out, and you're left with x to the n. And once you get rid of that log x, you can integrate x to the n. So that's a good deal, okay? Now, do I really do these? I usually look them up at a table, because it's just such a pain in the neck to do. But you, same principle here. I don't know the integral of an arcsine. I can take the derivative of it. I don't want to, but I can. And the arctangent. Both of those will work that way. So that's what you want to let to be the u, because you can take the derivatives. You can't take the integrals off. They're just miserable. I mean, I don't even know what gives you that as a derivative. So in these cases, unfortunately, your x to the n has to be your dv, which is going to get a little worse, but in every one of these cases, you wind up with something in the denominator that will help out with it. Okay. What if you had e to the x sine or e to the x cosine? It really doesn't matter. Because both of these, neither one of them get any better or worse when you integrate it. Okay? So it really doesn't matter. They suggest that u be the trig function and dv be the e function. Either one of them works pretty well. Okay? You might, I can't even swear that you'll do this. You might save one step by doing like that, but I can't even imagine for sure that you save a step. I think they're exactly equivalent, but it really doesn't matter on those. Now, in problems of repeated applications of integration by parts, like you have x to the n, you have either a sine, a cosine, or e as the second part. So you're going to step this down every time. And these just wobble around and go back and forth, okay? Therefore, you can use a tabular method, in which we're going to illustrate in the next example, to help organize the work. This method works as well for integrals, of this one, I thought that's what they were talking about. Repeated application of integration by parts. So it doesn't have to be these forms, but quite often it will be something like this. X to the n, and then something here that doesn't get any worse when you do the dv's, okay? So here's how you do. And you can go to larsoncalculus.com to see an interactive version of this kind of example. So let's do example 7. Find the integral of x squared sine to the 4th x dx. This is sine of 4x dx. This is not a bad thing to do just regular way. But here's how we use our table. Okay? This is how they do it anyway. The first column of the table, they put the signs. Okay? They alternate. Is it getting close to time? Did I forget to bring my watch in here today? I must have forgotten it. Again, my work study seal was moving everything around. It's what?
We still have like 20 minutes.
Oh, I thought so. I thought. Can't be that late. Okay. You alternate signs. Okay. So they start with plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. You're not going to need that many, but I'll just put them down there. Okay. The next column, you do the u and its derivatives. Okay? And then the third column, you put the v prime and its antiderivatives. Okay. So, in this case, which would be your u? X squared. So we put the x squared here. Now the v prime we'll put up here, okay, and that's going to be sine of 4x. Not going to use it, but we'll put it up there. Okay. So let's do the derivative of sine of x squared. What does that give you? Sine of x squared. Pretty easy, folks, huh? X squared. No, I'm sorry. Derivative of x squared. I'm saying it wrong. Sorry about that. Okay. Derivative of x squared. Duh. 2x. Derivative of 2x. 2. Derivative of 2. 0. All right. Now, antiderivative of sine of 4x. What would that be? In other words, you integrate that. Negative cosine of 4x divided by 4. That's all you have to do. Chain rule it, basically. That's a very lousy way to say it, but okay. Antiderivative of minus cosine. Say again? Minus sine of 4x. This time it's over 16 because you got another over 4. And the next one we really don't even have to write down because it's going to be multiplied by 0. So I don't have to do that. Okay? So here's what we do. Oh my goodness. The 10 o'clock scholar. Okay. Good deal. Josh is here. We're only missing Tiara. Okay? Then we would be a queen, wouldn't it? No. Okay. Okay. So now we write down our answers. I mean, this is all there is to it. It's you write down on the diagonal. Okay? And that would be x squared or minus x squared cosine 4x over 4 minus a minus is plus, okay, minus here, plus, minus, that would be plus 2x sine 4x over 16, but then the 2 will go into that and make it an 8. And then we finally have a plus. Oh, I didn't need to write down one more. Sorry, because that has to have something under it. What's the antiderivative the derivative of sine 4x? Minus sine 4x over 16. Cosine 4x over 64. Yeah, sorry, because I need something to multiply that 2 by. So that would be a plus 2 cosine 4x over 64. 2 will go into 64, 32. Okay? So here's what we've got. Now, they're going to leave all the fractions in there. So this, at the very beginning, becomes a minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1 over 32 cosine 4x plus c. All right. So when you're doing this, put down your alternating signs. Always start with plus, plus 1, plus 1, plus. Okay? Then put down your derivatives until you get to 0. And then put down your d prime, whatever the other side of this was. There was your u, there was your v prime. And write it down here, the v prime here. Then do its antiderivative, this antiderivative, and do the antiderivative that goes across from the 0. You're not going to multiply it because you multiply on the diagonal. So this one times that, this one times that, this one times that. And if you have the signs here and keep up with the signs here, they take care of themselves. And sure enough, you have it. And just don't forget to do a plus c at the end. Is that what they got? Minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c. Good deal. Any questions? All right. Homework exercises would then include any of the odds, 5 through 9. They're all at Calc Chat, 5's at Calc View. Remember they said the more you practice on these, the better you get at them. That's true for everything, by the way, folks. Either 11 or 13, they're both at Calc Chat. 11's at Calc View. Any of the odds, 15 to 33, they're all at Calc Chat. 15's at Calc View. 35 or 37, they're both at Calc Chat. 39's at Calc Chat. 41's at Calc Chat. Then any of the odds 43 to 51, they're all at Calc Chat, but 45's at Calc View. Any of the odds 53 to 57, they're all at Calc Chat, 55's at Calc View. You can explore doing either 59 or 61. They both should be at Calc Chat. Then you can do either 63 or 65, they're both at Calc Chat. 67 should be at Calc Chat. 69 should be at Calc Chat. And then any of the odds, 71 to 75 should be at Calc Chat. Any of the odds, 77 to 81 should be at Calc Chat. And basically you use what you did in 71 to 76 when you're doing 77 to 81. So, wow. Okay, either 83 or 85, they're both at Calc Chat. 87 should be at Calc Chat. 89's at Calc Chat. And 91's at Calc Chat. 93's at Calc Chat. 95's at Calc Chat. And 95's at Calc Chat. Now 99 says finding an error, so I really don't like those too much because they printed something in here incorrectly. I hate for them to do that, but you see if you can figure out why 0 is not equal to 1, okay, in that case. Any questions on those? All right. Oh, I forgot to show you how they did. Example 7, I forgot. Okay, did it the same way we did, They didn't write down as many pluses and minuses, but write as many as you need to. Write down u and then all its derivatives till you get to 0. Be sure you write it down. You're not going to use it, just like you're not going to use the sine 4x up here. You write the dv, which is sine 4x. You always need the dx in it. Write that here. Then take the antiderivative of that, antiderivative of that, antiderivative of this, until you're across from your 0 here. Once you're across from it, you're fine. Because you're not going to use this one or that one. You're going to do down the diagonal plus this times that. Well, that's plus minus. That's going to be a minus 1/4 x squared sine 4x. Minus a plus and a minus. That's going to be a plus 2x, but the 2 will cancel into the 16 and be at 8. So that would be plus 1/8 sine 4x. Then you're going to do a plus this times this. All three are pluses, but the 2 will go into 64/32. So 1/32 cosine 4x. We wouldn't have done to continue because that would be all zeros over here. So you're done there except for adding the plus c. Yeah, if this is a indefinite integral, which of course it was. Okay, sorry I forgot to show that. The solution is obtained by adding the sign products of the diagonal entries, and that would be minus 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c at the end. That is the last slide in the section. I should have done that before I gave you the homework problems, but I forgot to. Where? Yes.
Can you talk about the NASA program, people that work here?
Okay, not a whole lot about it. It's the NASA Community College Aerospace Scholars Program. The NCAS is written there, but there's not really much information about it. That's what it stands for. This piece of paper tells you some links that you can go to find out more information, to get the application, and to do all the things like that. You're certainly welcome to take this piece of paper if you want it. The deadline to apply is October 16th, which is a little over 1 week away from now, right? Today's the 7th. This is 9 days away. It's a week and a half, almost, not even that. Okay? So, if you want to know more about it, talk with Fred. He's a good guy. He's participated in the program. He knows it. Okay? Yes?
I was also part of NCAS as well.
I'm sorry?
I was a part of NCAS as well.
I can't hear you.
I was a part of NCAS as well.
Oh, you were?
Yes.
Oh, I see. Okay, I didn't know that. Fantastic. What did you think of it?
I thought it was fun. I did the same thing Fred did, except I was an engineer. I put the rover together.
Uh-huh. All right. Oh, were you in the same thing?
No.
Oh, okay. Different classes. Okay. Yeah. It's a great program. I mean, it is a tremendous program. So talk with either of these two. Any of the others have you been in it? Okay. What's that? Okay. A fantastic program. Now, people have asked me about it a couple times. Is there any stipend with it? And there's not, is there? No. You just do it. Do they pay travel, though? Like when you go to do the travel. And they'll take care of that. They'll house you, feed you, all that. So it's no cost to you except time. And so that's the fun part, right? Right. Okay. So it's a great program. All right. What had happened, my pen knocked my flash drive and it disconnected. So let me see if I can get it back. No, I can't get it back. Why is it not coming back? Okay, let me try again. This is rather bizarre. Where is my flash drive? Okay, I'm going to pull it out. Let's see if it even recognizes it's got it in there. Yeah. Nope, it's not recognizing it's in there. This was a freebie from the STEM program. I hear it. There it recognized it. All right, let's go back to Larson Calculus. And 8.3 is where we are. All right, we've got what? 8 more minutes? Is that all? Sorry about that. Okay. All right, Chapter 8 is still integration techniques primarily and improper integrals, which we'll do maybe a little bit at the end. 8.3 is trigonometric integrals, trigonometric integrals, okay? We will solve some trigonometric integrals involving powers of sines and cosines. We'll solve trigonometric integrals involving powers of secants and tangents. And we'll solve some trigonometric integrals involving sine-cosine products. Okay, this will be a flashback to trig here, folks. Integrals involving powers of sines and cosines. In this section, you'll study techniques for evaluating integrals of this form. Integrals of sine to the nth power of x times cosine of the nth power of x. Notice the arguments have to be the same, because the exponents are different. And in the next group, we'll do secant to the nth, tangent to the nth. Again, the argument's the same as these, but the exponents are different. Now, this is where either m or n is a positive integer. No fractions, no decimals, no negatives. Positive integers. Okay. To find the antiderivative for these forms, let's try to break them into combinations of trigonometric integrals to which you can apply the power rule. Basically, a U substitution in the power rule. That's what we're going to be gunning for when we can do it. And when we can't do it, they'll show you some other techniques. One we've already used. For instance, you can find the integral of sine to the 5th x cosine x dx. You don't have to do anything. How would you do that? How would you proceed with that? Anybody? Sort of gave it away when I said you'll use the
power rule.
Yeah, U substitution of the power rule. Or you can do the power rule directly if you want to. If you let U equal sine x, du is cosine x dx, right? And this will be U to the 5th du. That's just a power rule, okay? Pretty straightforward. And that's what they said. U equals sine x, du is x cosine x, then you have integral of U to the 5th, and that's U to the 6th over 6 plus c. Then plug back in what U is. U is UR, whatever. Sine x is sine to the 6th power over 6 plus c. So, that's when we can do it, that's what we'll do. So to break up the integral of sine to the nth x cosine to the nth x dx into forms which you can apply that power rule using this type thing, here's the relationships. Okay? Now these are some of our favorites, right? We know that one, right? Sine squared plus cosine squared is equal to 1. Hang on to that. We use it a lot. Now here's the one we did last time. This one was sine squared, wasn't it? 1 minus cosine 2x over 2. Remember how we got it to? And when it's cosine x, almost the same thing. You just add those two together. add this one to the cosine 2x formula, and you lose your sine squareds, and you get only cosine squared. So that's why it's 1 plus this divided by 2. Okay? Those are called power reducing formulas for sine squared and cosine squared. So those we've already used. All right. Now that's what we're going to do. What do we look for to do it? Guidelines. That's what we look for. And here's what they are. When the power of the sign is odd and positive, or, okay, we're only letting them be positive, so that's almost redundant, but odd and positive. Save one sign by itself, and then you have an even, right? You have sign to an even factor. Convert the remaining factors into cosines, then expand and integrate. So here's what we're talking about. If that m, which is what the sign was, is an odd number, break it into a 2k plus 1. So give me an odd number. Make up any odd number. 3. Okay? So you'd say 2 times 1 plus 1. Right? That makes 3, right? Okay. Give me another odd number.
23.
23. Then you would use 2 times 11 plus 1. Right? So that's what you do. You do if it's an odd number, subtract 1 from it and then half it. Okay? 23, subtract 1, 22, half that, and get 11. Okay? So that's what you have. That's an odd number. And cosine, doesn't matter what cosine is. Doesn't matter if that ends even, odd, or whatever. It does not matter. Now, pull out one of the odd sign, the odd one that was there. And that leaves you 2k here. We'll keep the 2 with the sign and the k outside of that. Sine squared raised to the kth power is sine to the 2k power, right? They're sort of doing two things at once, but that's okay. The cosine we're leaving just like it is. And then that one sign that was here, just put it with the dx. Okay? Now why? Because this is the derivative of cosine, isn't it? Sine is the derivative of cosine. With the sine or something in there, your SIGN sign. Okay, this you can express in terms of cosines, right? Cosine squared is 1 minus cosine squared. Right? So this will be in terms of cosine. This is already in terms of cosine, and this is the derivative of cosine. So you got everything you need in terms of cosines, or its derivatives. So this will be 1 minus cosine squared x to the kth power. Now if that was an 11, like my student over here wanted, then that, you got a real big problem there, but it's just doable. You just have to raise that to the 11th power. So let's not do it to the 11th power. But as long as they're reasonable, you can still do it. It's not that impossible to do. It's just a pain in the neck to do. Okay? And this will be whatever power that is, and this will be your d cosine. Now, and you can do that. We will do that. When the power of the cosine, though, is odd and positive, you can do the same thing. Pull out that odd cosine, and let that be a cosine x dx. Then the rest of it will be even, and put the 2 with the cosine squared, and the k out here, 2k plus 1. So in other words, subtract 1 from it and divide by 2. The 2 stays here, the k goes here, and the single one goes out there. And then it doesn't matter what that sign is. It can be positive, it could be even or odd. It doesn't really matter. Okay? And this then becomes 1 minus sine squared raised to the kth power. As long as that k is not too awfully big, you can do that. But even if it is big, you can still do it. It just gives you big numbers. Okay. And then this is the derivative of sine. Now, okay, what if both powers are even and non-negative? All of them are non-negative, by the way, here. But what if both of them are even? Okay? And non-negative. then make repeated use of one of these two formulas. Okay? And what you do here, this is a power reducing formula. So if they're even to begin with, just keep reducing the power by this. Okay? Or that, whichever one, to convert the integrand to odd powers of the cosine. Then proceed like you did here. So now you're everything in terms of cosine. Okay? So, sounds like a lot of blah, 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 and it also sounds like we must be out of time. Is that right? We'll start example 1 next time. Okay? We didn't get far enough for new homework exercises here, but we will pick up and go from this point. All right. Good deal. Any questions? By the way, Devin asked for it, and I'm going to try to deliver soon. The trouble is I've got 2 huge deliverables that are coming up very soon. As soon as I can get at least the first one knocked out, I'm going to try to get to the second, to get the WebAssign code for you. So I've got it. I just have to publish it. I've got to find what they did with it. Okay. And why did I do what I just... Oh, I know. Okay, good deal. We'll see you then on Wednesday. Oh, I forgot to make these announcements. I was going to, and then I completely forgot. My office hours get a little screwed up this week. For instance, tomorrow morning, I normally have office hours from 9:45 until 11:30. However, tomorrow I'm taking my afternoon class on a field trip, so I've got to, at 9:45, go to the Birmingham campus, pick up the van, and bring it back here. So there goes most of those office hours. I will be back here before 11:30, but it won't be for very long. And then later in the day, I'll be taking the van back, so I won't be hanging around much in the afternoon either. Okay, so that's Tuesdays. Okay? Thursday, I might, well, it won't mess with my morning office hours. I may leave a little early because I've got to go out of town Friday, and that means Friday I'll have no office hours on the Birmingham campus on Friday. I'll be out of town. I haven't made the request yet, but I've got to do that. I've got to do it this morning. So, see you then. Wednesday.
You should offer field trips for all of your classes.
I'm sorry?
You should offer field trips for all of your classes.
I can't hear you.
You should offer field trips for all of your classes.
Cool. So I heard all these classes, but I didn't hear the first one.
I said you should offer a field trip for all of your classes.
Okay. Sure I should.
I didn't give you
They're paying enough for just one, so since I have 8 classes,
you can give me bonus points for showing up for what? Your science class? Your science class got a field trip?
it's physical science, and you can't take it. You need to take physics. You're a pre-engineer. Oh, too late. All right, let me see what I can find. Cal 2, Test 1. I think I'm close. I'm close, but not there. Ah, here we go. Test 1. All right. Okay, 13.1.